Welcome to DAR Tutors. Today, we will explore energy cycles and chemical reactions, a fundamental concept in IB chemistry higher level. By the end of this lesson, you will be able to explain how energy is absorbed when bonds break and released when bonds form, calculate enthalpy changes using average bond enthalpy data, and apply Hess's law in the context of bond enthalpies. These are essential skills for solving complex thermodynamic problems in the IB syllabus. Our central guiding question will be, how does the application of the law of conservation of energy help us to predict energy changes during reactions? Let's begin by addressing a common misconception. It is a common mistake to think that energy is released when bonds break. However, the opposite is true. Energy is always absorbed when chemical bonds break. Work needs to be done to overcome the attractive forces holding the atoms together. Let's visualize this with a simple covalent molecule. Here we have a hydrogen molecule. The two hydrogen nuclei are attracted to the shared pair of electrons between them. This attraction is what creates the chemical bond. To break this bond and separate the atoms, we must overcome this strong electrostatic attraction. This requires an input of energy from the surroundings, making the process endothermic. Energy is absorbed to pull the atoms apart against their attractive force. Bond breaking is therefore an endothermic process. Its reverse, bond making, must logically be exothermic. When atoms come together to form a bond, energy is released into the surroundings because they are settling into a more stable, lower energy state. This fundamental principle, that energy is absorbed to break bonds and released to form them, is the basis of our entire discussion. Now, let's look at this principle in more detail using molecular orbital theory, which provides a deeper understanding of bonding. While the Lewis model is useful, molecular orbital theory addresses some of its deficiencies. In molecular orbital theory, atomic orbitals from interacting atoms combine to form new molecular orbitals that span the entire molecule. For a hydrogen molecule, the 1s atomic orbitals from each atom interact. This interaction produces two molecular orbitals, a lower energy bonding orbital, denoted as sigma, and a higher energy antibonding orbital, denoted as sigma star. The electrons then fill these molecular orbitals starting with the lowest energy level, according to Hund's rule and the Pauli exclusion principle. For the H2 molecule, the two available electrons from the atomic orbitals fill the lower energy sigma bonding orbital. The higher energy sigma star antibonding orbital remains empty. When these electrons enter the lower energy bonding orbital, the molecule becomes more stable and energy is released. This release of energy is the bond energy. The bond order, a measure of the number of bonds between two atoms, is calculated using the number of bonding and antibonding electrons. For the H2 molecule, we have 2 electrons in a bonding orbital and 0 in an antibonding orbital. The bond order is 1. This confirms our understanding of a single bond between two hydrogen atoms, but provides a more rigorous quantum mechanical explanation for the energy release during its formation. Based on this energy principle, we can now define bond enthalpy. You will be able to use this data to perform calculations. Bond enthalpy, often denoted as H with a superscript circle for standard conditions, is the enthalpy change required to break 1 mole of a specific type of covalent bond in the gaseous state. So, for a diatomic molecule XY, its bond enthalpy is the energy needed to break 1 mole of these molecules into their gaseous atoms. Since it's bond breaking, the value is always positive, indicating an endothermic process. For example, to break 1 mole of HH bonds in hydrogen gas to form 2 moles of hydrogen atoms in the gaseous state requires 436 kilojoules. This means the bond enthalpy of an HH bond is plus 436 kJ per mole. It's important to understand that the size of the bond enthalpy value is a direct measure of the strength of the bond. A larger bond enthalpy means more energy is needed to break the bond, and therefore, the bond is stronger. In the IB Chemistry Data Booklet, you'll find a table of average bond enthalpies. It's crucial to distinguish between single-value bond enthalpies and average bond enthalpies. A value like plus 159 kJ per mole for the FF bond is an exact single value because F2 is the only molecule containing an FF bond. However, a bond like a CH bond exists in thousands of organic molecules, and its strength can vary slightly from one compound to another due to its chemical environment. Therefore, the data booklet provides an average bond enthalpy for the CH bond, which is a representative value derived from many compounds. This average value is an excellent tool for estimating enthalpy changes. We can use these average bond enthalpies to calculate the enthalpy change of an entire reaction. This is one of the most important applications of this concept. The logic is simple. A chemical reaction is just a rearrangement of atoms. We can imagine the process happening in two steps. First, we break all the bonds in the reactants, which is an endothermic process and requires energy. Second, we form all the new bonds in the products, which is an exothermic process and releases energy. The overall enthalpy change of the reaction, according to Hess's law, is the sum of the enthalpy changes for these two steps. This gives us our key formula. The enthalpy change of the reaction equals the sum of the bond enthalpies of the bonds broken, minus the sum of the bond enthalpies of the bonds formed. Let's apply this to an example. We will calculate the estimated enthalpy change for the complete combustion of methane. The balanced chemical equation is CH4 gas plus 2 moles of O2 gas react to form CO2 gas and 2 moles of H2O gas. The first step is to identify all the bonds broken. In methane, we have 4 CH bonds. In the 2 oxygen molecules, we have 2 OXO double bonds. So, the total energy absorbed is 4 times the CH bond enthalpy plus 2 times the OSO bond enthalpy. Next, we identify the bonds formed. In 1 CO2 molecule, there are 2 CEO double bonds. In 2 H2O molecules, there are 4 OH single bonds in total. So, the total energy released is 2 times the CO bond enthalpy plus 4 times the OH bond enthalpy. Using values from the IB data booklet, we find the total energy absorbed is 2652 kJ, and the total energy released is 3460 kJ. Applying our formula, the enthalpy change is 2652 minus 3460, which equals 808 kJ per mole. The negative sign confirms the reaction is exothermic. Let's work through another example. You will be able to calculate unknown bond enthalpies from reaction data. In this problem, we're asked to find the bond enthalpy of chlorine, given the bond enthalpies of hydrogen and hydrogen chloride, along with the overall enthalpy change of the reaction. We will reverse our previous method to solve for the unknown. We'll use our bond enthalpy formula. First, let's list the bonds broken and formed. On the reactant side, we break 1 HH bond and 1 Cl bond. On the product side, we form 2 HCl bonds. Now, we substitute the known values into the formula. The enthalpy change is 184. The bonds broken contribute 436, plus the unknown Cl bond enthalpy. The bonds formed contribute 2 times 431. Let's call the Cl bond enthalpy X. This gives us a simple algebraic equation. Simplifying the right side, we get 436 minus 862, which is negative 426. So negative 184 equals X minus 426. To solve for X, the Cl bond enthalpy, we add 426 to both sides. The result is positive 242. This calculation allows us to determine an unknown bond strength from reaction data. In the IB data booklet, the actual value for the Cl bond is indeed 242 kJ per mole, showing the accuracy of this method. Now, let's address the accuracy of these calculations. You will understand why calculations using average bond enthalpies may differ from experimental values. Our previous calculation for methane combustion yielded an enthalpy change of 808 kJ per mole. The experimentally accepted value is 810 kJ per mole. The difference is minor, but it's important to remember that bond enthalpy calculations provide an estimate, not a precise value. Why is there this difference? The key is that we use average bond enthalpies. As we've discussed, the strength of a CH bond, for instance, isn't exactly the same in every compound. The actual CH bond strength in a methane molecule is likely slightly different from the average CH bond strength. The bond enthalpies used are averages. The real bond enthalpies in the specific molecules involved in a reaction will likely vary from these average values. Because we are using an average, our calculation is an approximation. Another important consideration is the phase of the substances. Bond enthalpy values are defined for reactions involving gaseous molecules. If a reactant or product is not in the gaseous state, its enthalpy of vaporization or sublimation must be factored into the calculation. You will be able to perform these calculations. Consider the combustion of liquid ethanol. Here's the equation. Given ethanol vaporization enthalpy equals plus and 4 kJ per mole. First, we calculate the enthalpy change as if all species were gases. This involves breaking the bonds in one ethanol molecule and 3 O2 molecules, and forming bonds in 2 CO2 and 3 H2O molecules. The formula for this is the sum of bonds broken minus the sum of bonds formed. After calculating the bond breaking and bond forming energies, we find an enthalpy change of 1263 kJ per mole, assuming gaseous ethanol. However, the problem specifies liquid ethanol. We are breaking bonds in liquid ethanol. This means we first need to input the energy required to vaporize it. This vaporization step requires 44 kJ per mole of ethanol, and it's an endothermic process. Therefore, we must add this energy to our overall enthalpy change. The final corrected enthalpy change for the combustion of liquid ethanol is 1219 kJ per mole. Let's explore another factor that affects bond enthalpy: ring strain. This is particularly relevant in organic chemistry. Ring strain occurs in small cyclic molecules, like cyclobutane, where the atoms cannot achieve their ideal bond angles as predicted by VCPR theory. For example, VCPR predicts a tetrahedral carbon atom should have bond angles around 109.5 degrees. In cyclobutane, the bond angles are forced to be close to 90 degrees. This deviation from the ideal angle weakens the carbon-carbon sigma bonds because the atomic orbitals cannot overlap as effectively. A weakened bond means less energy is required to break it. Indeed, a typical CC single bond has an average enthalpy of 346 kJ per mole. But in cyclobutane, the bond enthalpy of the CC bonds is only 272 kJ per mole, significantly lower due to the ring strain. This is a real-world example of how context affects bond strength. This phenomenon isn't just an academic curiosity, it has profound implications in biology. For instance, the beta-lactam ring is a key structural feature of penicillins, a class of life-saving antibiotics. This four-membered ring has significant ring strain. The ring strain in the beta-lactam makes its CN bond easy to break. This allows penicillin to effectively disrupt the cell wall synthesis in bacteria, killing them. So, a seemingly simple chemical concept of ring strain is at the heart of one of modern medicine's greatest achievements. Bond enthalpies also help us understand chemical reactivity. You will be able to explain how carbon-halogen bond strength affects reaction rates. Consider the hydrolysis of halogenoalkanes. This is a nucleophilic substitution reaction where the halogen atom is replaced by a hydroxyl group. In an experiment, you might compare the rates of hydrolysis of 3 halogenoalkanes, 1 chlorobutane, 1 bromobutane, and 1 iodobutane. The rate of the reaction can be monitored by timing how long it takes for a precipitate of the silver halide to form after adding silver nitrate. What do we observe? The reaction with the iodoalkane is the fastest, followed by the bromoalkane, with the chloroalkane being the slowest. To explain this trend, we look at the bond that is broken in the first step of the reaction, the carbon-halogen bond. In this reaction, the C-hal bond must break. The strength of this bond is therefore a critical factor in determining the activation energy and thus the reaction rate. Let's compare their average bond enthalpies from the data booklet. We find that the CCl bond is the strongest, with an enthalpy of 346 kJ per mole. The CBr bond is weaker at 285 kJ per mole. The CI bond is the weakest at 218 kJ per mole. And here's the explanation for the observed reactivity. Since the CI bond is the weakest, it requires the least energy to break. This means the activation energy for the hydrolysis of the iodoalkane is the lowest, and therefore, it reacts the fastest. The stronger CCl bond requires the most energy to break, leading to the highest activation energy and the slowest reaction rate. This clearly demonstrates how bond enthalpy is a powerful tool for predicting and explaining chemical reactivity. We can also use bond enthalpies to make predictions about homologous series. You will be able to explain the trend in enthalpy of combustion for alcohols. Let's consider the enthalpy of combustion for the homologous series of monohydric alcohols. Methanol is CH3OH, ethanol is C2H5OH, propan-1-OL is C3H7OH, and so on. We can predict the trend by analyzing the change in bonding for each additional methylene or CH2 group. From ethanol to propan-1-OL, we add one CH2 unit. This means we break one extra CC bond and two extra CH bonds in the reactants. We also form two extra CO bonds and two extra OH bonds in the products. Let's calculate the net energy change. Breaking these bonds requires 1174 kJ of energy. The corresponding bonds formed are two CEO bonds and two OH bonds, releasing 2534 kJ of energy. The net change is 2534 minus 1174, which is 1360 kJ per mole. So, adding one methylene group makes the reaction 1360 kJ more exothermic. Therefore, the enthalpy of combustion becomes more exothermic, more negative, as the number of carbon atoms increases in the alcohol homologous series. This is a linear trend because each additional CH2 unit contributes a fixed increment to the energy released. This is a powerful demonstration of how bond enthalpy data can be used to predict macroscopic trends in chemical properties. This predictive capability is one of the hallmarks of a good chemical model. Take a moment to think about why we are subtracting the energy absorbed to make bonds and adding it to the overall enthalpy in this specific calculation. We've now established a solid foundation in using bond enthalpies. Before we tackle IB-style problems, here's a word from our sponsor. Contact our tutors for expert tuition in IB, A-level, and IGCSE curricula. Let's apply what we've learned to some IB-style practice questions. These are designed to test your understanding at the HL level. You will be able to solve complex problems involving multiple bonds. Question 1 involves the hydrogenation of cyclobutene to cyclobutane. We need to estimate the enthalpy change. First, we look at the bonds that change. A C-C double bond and an HH bond are broken. In their place, one CC bond and two CH bonds are formed. Notice that all other bonds in the ring remain unchanged, so we don't need to consider them. Plugging in the average bond enthalpies, we calculate the energy absorbed from the broken bonds and the energy released from the formed bonds. The result is 124 kJ per mole. This estimate is exothermic, as expected for a hydrogenation reaction. Take a moment to check your calculation. For question 2, let's look at the combustion of ethene. In the reactants, we break one C-C bond, four CH bonds, and three OSO bonds. In the products, we form four CO bonds and four OH bonds. We can then substitute the values. This gives us an enthalpy change of 1304 kJ per mole, which is a highly exothermic value consistent with a combustion reaction. Again, note how systematically breaking down the problem into bonds broken and bonds formed leads to the correct answer. Let's continue with two more problems. These will require you to apply our formula in slightly different ways. Question 3 asks for the enthalpy change of a substitution reaction between methane and chlorine. Analyzing the bonds, we see that one CH bond and one ClCl bond are broken. They are replaced by a new CCl bond and a new HCl bond. Using our bond enthalpy formula, we find the total energy absorbed is 656 kJ, and the total energy released is 727 kJ. The enthalpy change is 656 minus 777, which gives us 121 kJ per mole. This reaction is exothermic. For question 4, we have a bond-breaking reaction, the pyrolysis of butane. This will be endothermic. Let's draw out the structures. In butane, we break one CC bond in the middle and one HH bond. Wait, no, that's not right. Let's re-examine the question. pH 10, C2H6 plus C2H4. In the reactants, butane has 3 CC single bonds and 10 CH single bonds. In the products, ethane has 1 CC bond and 6 CH bonds, and ethene has 1 COC double bond and 4 CH bonds. We break 3 CC bonds and 10 CH bonds and form 2 CC bonds, 10 CH bonds, and 1 CC bond. Notice we break and form the same number of CH bonds, so their contribution cancels out. We are breaking 3 CC bonds and forming 2 CC bonds and 1 CC bond. Calculating the values, we find the reaction is endothermic, requiring an input of 124 kJ per mole of butane. This makes sense, as this is a pyrolysis reaction that requires high energy. The enthalpy change is plus 124 kJ per mole. It's a key skill to carefully count the bonds and determine which are broken and which are formed. I apologize, my arithmetic was incorrect. Let's recalculate. The bond breaking is 3 times 346, which is 1038. The bond forming is 2 times 346 plus 614, which is 692 plus 614, or 1306. The difference is 1038 minus 1306, which is negative 268 kJ per mole. So this reaction is exothermic. This highlights how crucial careful calculation is. We have one final problem, which is an excellent test of your algebraic skills and understanding of the bond enthalpy formula. Question 5 gives us the overall enthalpy change for the reaction of iodine and chlorine to form iodine monochloride. We are given the bond enthalpies for II and C-alkyl, and we need to find the enthalpy change for the alkyl bond. As before, we apply our bond enthalpy formula. We break 1 II bond and 1 Cl-Cl bond. We form 2 I-Cl bonds. Let's substitute the known values. The enthalpy change is given as 70.2. The sum of the broken bonds is 151 plus 242. We'll call the unknown ICl bond enthalpy Y. The equation becomes negative 70.2 equals 393 minus 2y. Now we rearrange the equation to solve for y. Adding 2y to both sides and 70.2 to both sides, we get 2y equals 463.2. Finally, we divide by 2. The bond enthalpy of the ICl bond is calculated to be 231.6 kJ per mole. This problem demonstrates how bond enthalpies can be a powerful analytical tool, allowing us to deduce unknown bond strengths from experimental reaction data. You will find that the actual value for the ICl bond is indeed around 232 kJ per mole. Let's quickly recap what we have covered today. These are the key takeaways you should master for the IBHL chemistry exam. We began with the fundamental principle that energy is always absorbed when chemical bonds break, an endothermic process, and energy is always released when new bonds form, an exothermic process. We saw how average bond enthalpies can be used in conjunction with Hess's law to estimate the enthalpy change of a reaction. The key formula is the sum of bonds broken minus the sum of bonds formed. We discussed why these calculations provide estimates. They rely on average values and do not account for ring strain or phase changes. For accurate calculations, vaporization enthalpies must be included for non-gaseous reactants. And finally, we practiced applying these principles to a variety of IB-style problems, from combustion reactions to determining unknown bond strengths. The ability to systematically apply the bond enthalpy formula is crucial for success. Mastering energy cycles in reactions is essential for understanding how and why chemical reactions occur. Thank you for joining.